CVPR was this week, and a ton of cool papers came out, obviously all related to computer vision. Go check them out. There's a lot of really cool papers. This was one of the highlights called CoDeF, and I kind of want to just, like, this will probably be a quick video. I kind of just want to go over the main idea behind it. There's a lot of little tricks that they do. If you're curious, go check out their code. And the nice thing is that you have code, so you can go and use this. But it's very different from other architectures in what they're trying to do and how they do it. It's kind of like a nerf, so it's lightweight, and it's very, it's different. It's different from other normal things, as opposed to just throwing a ton of parameters. This thing is trying to use like a few parameters and make it fast. So basically the idea is we have a video and we want to do style transfer on that video. And obviously, if you use a dense network, that's going to be a very difficult task. So the idea is basically we have a set of frames. So some set of frames here. This will be length by width by t. And we want to transform it into some other set of videos. Length by width by t. So some style transfer task. Now this has been done with images for a while, and it's been attempted with videos for a little bit. Less time than images, because images are much easier. But one problem is it's not just a simple transfer from style A to style B. It's transfer from style A to style B, but keep things consistent. So like I can't just take my first video and transform it. Like this, I don't know, this video here, where they transform it from, I don't know, a natural scene to some, I don't know, futuristic cool looking scene, or the other way around, like some artistic scene to some natural scene. Like you can't just take each frame and translate it, because that's going to be inconsistent with the translation. Like if I take one frame and then translate it and take the next frame and translate it, the problem with that is you're going to get inconsistencies in the output video, because the output video isn't informed of every frame together. So if I just take this frame and translate it to this frame, and this frame, and translate it to this frame, like you're going to get garbage output, and that's usually what we see. So the main issue is, like, you can do this with Stable Diffusion, where you just translate frame to frame. But the main issue is that we want it to be consistent. So they have this lightweight way of making it consistent. Now, there are limitations, and describing the method, you can probably see what the limitations would be. But I think it's a really cool start, and I think what they do, I think what they do is cool. So I'll just go over the main idea. So the main idea is they use this lemon video exploding. Maybe I'll do something with like a ball. So I have this set of frames here. So maybe I have this ball that's going to be moving in time. So that's time, and this is our video. So I have this ball that's just moving along some trajectory. There, that's good enough. So some ball moving along a trajectory, and this is my video where t is equal to 5. I have 5 frames. It's a very low quality video, but it'll do. So the idea is we can basically break this into 2 parts. We can break this into a canonical representation, a canonical image that basically represents the entire video. So like all the information in the video, and then we can also we can take the information part and we can take the movement part, and we can basically make those orthogonal to, like, they're basically orthogonal to each other. So you can basically extract those 2 parts from each other. So what would be the canonical representation? The canonical representation of this would just be a ball. So this is our canonical image. This right here. This canonical image is going to be our representation for this whole video. Now, obviously, this doesn't have any movement. This is just our canonical frame. Now, what we're going to do is we're going to train something to represent this canonical image, so a nerf in some way. This will be x, y inside some network, so some network with some parameters will be translated to some RGB values. And basically, this is saying I'm going to take the pixel 0, 0, and it's going to give me RGB values for that. and maybe this will just be white. And if I take this, I don't know, some pixel like right here, then this will be all black. So that's the idea. Just normal nerf style. So this will be our canonical representation of our video. Now we need a movement module, and we're also going to train a network to basically represent the movement in here. Now, the way they represent movement is a little weird at first, but it's cool how they do it. So basically we're going to say, let's just start off with one frame. For each pixel in this frame, we're going to have it query our canonical image. So in this case, we want a ball right here. Now, all we have is we have XY coordinates here, and we have XY coordinates here, which we can get from our network. Now what we're going to do is we're going to take XY coordinates from our frame 1. So frame 1 is going to give us some XY coordinates. And we're going to put this through some movement network. I'll call this d theta, and this should actually be c theta for canonical. And what this is going to do is it's going to give us a x prime and y prime. And what this x, y, and y prime represent is basically the pixel we want from our canonical image to be put in this frame. So for these pixels, it doesn't really matter, but for, say, this pixel right here, the pixel in the middle of the ball, I'll draw it in red rather. So some pixel in the middle of the ball, this pixel is going to be sent through this this movement network, and it's basically going to say, I want this pixel in the canonical frame. So it's going to take those pixel values and it's going to copy them into our image here. Now, for this frame here, the ball is in a different place, but the idea is that this pixel stays the same here. So this pixel in the middle of the ball here is the same pixel as the one in the middle of the ball here. So the movement module should take whatever this XY coordinate is here. We'll call this maybe AB. AB at time 0, so t is equal to 0. Send this through the movement module, and it should give us this middle point in the ball, if we're querying the point in the middle of the ball. And that should be equal to the point in the middle of the ball here, which would be maybe C, D, and t is equal to 2. So the movement module is basically just querying our canonical image, or the movement module is basically taking pixel coordinates from the video, and it's querying the canonical image for the pixel that it wants. And intuitively, the way you can think about this is this represents all our features, and the movement module is just taking the features from there. And in this case, all of our features is just the ball in the background. So our movement module is just going to query the ball in the background and put it in the video based off the time step. Now, there are some limitations, and I'll talk about that. You can probably think of some right now. But on to actually formalizing this and how they do it. So to formalize this, they have this complicated diagram. The basic idea is we have this pipeline here. We have XYT. So what we're going to do is we basically want to reconstruct the output image, or not the output, the output video. And the way we're going to do that is we're going to say for each pixel in the output video at every time step, so X, Y, and T, or rather the input video, which we're just encoding into a movement module and a canonical image. So for each pixel in the video, we're going to just take the coordinates. So we're going to take the coordinates because that's all the data we're going to have during inference time. And what we're going to do is we're going to extract features from those coordinates. So you can just think about this as taking X, Y, and T coordinates. So like if this is our video right here, it's some point in the video, just some point in the video, like a point in this video over here, like the ball. So just some point in our video, some x, y, t coordinate. And what we're going to do is we're going to extract features. I'll talk about that a little bit, what the features are, but it's basically just like a discretization. Just think of it as like an expanded form of x, y, and t. And they do that just because, like, you can think of it like old machine learning where you do feature extraction first, and then you send this through your network. So this is just the feature extraction step, and just another representation of the x, y, and time coordinates. So once we have our features, we send it through this MLP, which is going to be our movement MLP, and they call that the deformation MLP. So we have our feature vector, we send this through the deformation MLP, and this is going to give us x, y, and y prime. And x, y, and y prime are going to be used to query the canonical image. Now, C is going to be another network we train, and all C is going to do is it's going to be, just like NERF style, it's going to take x, y coordinates, and it's going to map them to RGB values. So in this case, we have some point in our video. We're extracting some features, so we have some x, y, and t coordinate. We send this through the deformation MLP. The deformation MLP is going to say, hey, I know what point this is. I want to know what information is going to be at this point. And it says, these are the XY coordinates in the canonical image that I think represent this point. So maybe it queries this point right here. So this point on the lemon. It sends these XY coordinates to the canonical MLP, and the canonical MLP says, this is the RGB value at that point in the video. And it does that for every point in the video. And you just train this using normal L2 loss. So it's a simple idea, but it's cool. Now, instead of training a massive network that has seen every single representation of video and canonical image, this is a NERF style model. So what you're going to do is you're going to train this MLP to only represent this scene. So we basically initialize these two MLPs, and we're going to train them to fit this scene only. So all we do is we take our video, we're going to iterate over every single point in the video, and we're going to train it to just reconstruct the video using these two MLPs, the deformation and the canonical MLP. And that's all you're doing. And the cool thing about this training is it takes approximately 5 minutes, depending on how large your image is. For high quality videos, it takes like 5 minutes. And once you have that, you can basically reconstruct the scene during inference time within like 10 seconds or something like that. So you basically get this reconstruction of the video in a compressed form within 10 seconds, or after you're done training this thing. So the idea is we're taking this video, we're going to train these MLPs to reconstruct the video using a canonical image and deformation information by just querying x, y, and t coordinates. So x, y, and t coordinates in our video. And what that'll hopefully do is it'll hopefully give us a good canonical image, and that good canonical image will be it'll be able to reconstruct this video well. So what we're trying to do is reconstruct a video such that we have a nice canonical image. Once you've trained this, you can edit the canonical image, so such as this. And since your deformation module is just querying the canonical image, if you do a style edit to your canonical image, so this lemon here, if we do a style transfer just to the canonical image, and then you do inference on the deformation field, just like if you were going to reconstruct the initial video, then you're going to get this style transformed video. Because remember, all the deformation module is doing is it's just querying points on your canonical image. It's not doing anything more than querying points in the canonical image. So if you transfer the style of the canonical image, it's going to transfer the style of the video because you just have your deformation module, which reconstructs the video, querying the points from your canonical image. So it's a very cool idea. So in the case of this ball over here, if our deformation module basically reconstructed this, and this was our canonical image, all I had to do is change this to a blue ball, and it would change if I reconstruct it by querying all of our x, y, and t coordinates in our video. It would change the ball to blue in every single one, because the canonical image has a blue ball, and all the deformation module is doing is it's querying the points in this canonical image here. So that's the idea. Now, what they also do is they do some tricks here. I'll talk about them really quick. Basically, they have this trick here called 3D hash encoding for deformation field, and it's a way to discretize this video into multiple resolutions. I don't really want to get too much into it. I feel like it's a little convoluted, but the idea is, let's say this is our entire scene here. You can represent it in 3 coordinates, so you can represent it basically in a box. Just think of it as x, y, and z coordinates as opposed to x, y, and t. And what you can do is you can chunk up the box into, you can discretize the box. And you're discretizing along the spatial domain, so x and y, and the temporal domain. So that means that every box is going to contain some space and some time. So maybe every box is like 10 pixels by 10 pixels by 3 seconds in time, or 3 frames in time. So that's how you're discretizing it. And what you do is you take a point from your, I don't know why it's not erasing. That's weird. Okay, so you take a point, or whenever you're querying points, instead of directly feeding x, y, and t into your MLP, like I said, you do feature extraction before, and the features you extract, you do feed in x, y, and t into your MLP, but you also feed in the discretization here. And the way they do the discretization is they basically say like what box is it in, and then they look for the closest corners, and they use a hash map to basically represent those pixels, and they basically stack all the features, and they do a multi-resolution hashing. So it's basically discretizing this at multiple resolutions to inform the network, basically give it more information of where exactly is this module in the video, or where exactly is the point in the video. It gives it a better idea of that, instead of it having to directly find that and encode all the features in this video. So it's kind of a way to just give it more, or do some manual feature extraction instead of this lightweight MLP having to learn everything. So just to help out a little bit. So yeah, discretize it at multiple resolutions, and yeah, feed that into the the deformation MLP. So just normal feature extraction. They mention here. This is the 2D case, but yeah, basically you still have your X, Y, and T, but you also have these features here that you're going to feed. So feature extraction. So this is like the full pipeline here that I showed above. Basically, you do your feature extraction. You then feed this through the deformation MLP, and then you feed this through the canonical MLP. And what this will do is it'll give you the reconstructed pixel at that X, Y, and T. So this is going to be used for our loss function you'll see in a second. Basically, we're going to query every point X, Y, and T, and we're going to do an L2 loss saying this point should be as close as possible to the actual point that should be in that the video was. So basically querying every point in the video and training your network to reconstruct that point in the video. Normal reconstruction loss. Hashing. They also mention that they have this flow-guided consistency loss. So the idea with this flow-guided consistency loss is we can basically help the model out with this movement information, because it's hard for like a lightweight MLP to kind of learn all the movement information. Especially if you're trying to train this thing as fast as possible, you want to inform the model as much as possible with information you already know. And they use this model called Raft to basically extract the flow information. And flow is exactly how it sounds. It's just the movement information in the video. So what we're going to do is we're going to query all the flows. And for any flow, so for any trajectory in the video, what they do is they model the confidence, and they model the confidence here. Basically, they say if we look at the movement from the current frame to the next frame, and then the next frame, so if we go forward one frame and then we go backward one frame with the same model, this basically gives you a confidence. Because if you have, if this is a large error, then you can say, well, I'm not very confident that there's a lot of movement here. But if this is small, then you can say, oh, well, if this is like 0, then you can say, oh, well, I'm pretty confident that the Raft model thinks that there is movement here. But if this is very high, then that means that there's a lot of error moving forward and backward. And if there's a lot of error moving forward and backward, then Raft isn't very confident that there is a flow there, that there's movement there, because there's error. So that's just what this term is. It's modeling the error for Raft. Now the flow loss, basically we can calculate the flow here by saying, so this is the deformation model at time t at point x and y, and this is the deformation model prediction at time t plus 1, essentially, plus the flow. And what we're going to do is we're going to train it to, basically we're going to get the flow from the deformation model by looking at the current deformation and the deformation at the next frame, deformation at the next time step, and subtracting the two will basically give you this trajectory between the current and the next frame. And that trajectory is going to, basically you want to model that as a flow. And that flow is going to be what you get from the Raft model. And you multiply it by the confidence that we described up here, such that the more confident Raft is, the higher, the more likely there is an actual like movement at that part of the video. And if that is more likely, then you would want the loss to be weighed higher, such that the model basically can rely on that information more. And if it's not very likely that there's actual movement there, then this term will be weighed low, meaning that the model doesn't actually learn from that. Because if the model if Raft isn't confident, then we don't really want to train our model to learn off that information, because we're not confident that the model's confident. So that's the idea. Basically just informing it with movement information using a pre-trained model that already can look at movement information in a video. Canonical. So this here is basically saying if you have a video where there's weird movement in there, let's say some object appears and then disappears, but it's not really like a part of your video. Maybe there's like a tree here that appears here for a little bit and then it goes away. The deformation field will look weird. So what we can do is we can mask everything but the ball. And we do that for every frame. And you can do that using something like segment everything. And the idea is to just inform it with this mask information, such that it only models basically the ball. Now, one problem with that is the canonical image will basically be the ball, but since everything outside of the ball was masked out, you're going to get this extrapolation error where the ball is modeled well in the canonical image, but the extrapolated part, which is everything outside the ball, everything in the mask region, is going to be, extrapolated information. And neural networks suck at extrapolating, so you're going to get these weird artifacts. Now, what they do is they sample, say, to tackle this issue, we sample a number of points outside the region and train them using L2 loss with the ground truth color. So they basically sample points outside the mask to train it a little bit on that. And this gives us our final loss. So you have your reconstruction loss, your flow loss, and then your background loss. And the background loss is what I described a second ago, which is training using points from outside the mask to prevent this extrapolation problem. Now, I think that's about it. They do some experimentation, and they mention here, like, if you basically have to train this for every video, but once you've trained it for a video, you can do as much editing as you want to the canonical image or to the canonical frame, and that can give you whatever edits you want in your video, assuming you get a good canonical frame. So all you basically have to have a kind of small GPU. So they mentioned they use NVIDIA a 6000 GPU, and it only takes like 5 minutes. I played around with this a little bit, and yeah, you don't need that much VRAM. It's like maybe 5,000 gigs or something, or not 5,000 gigs, 5 gigs of RAM, maybe higher. So a 3090 is definitely enough to use this model for good resolution videos. And you train this thing once for 10 to 15, or from 1 to 10 minutes to get your canonical image and your deformation module, and then you can make edits to the video by editing the canonical frame. And to edit the canonical frame, they use a control net to just edit it, but you can edit it any way you want. You just have to edit it, and then it projects the edit to every frame using the deformation module. Now, yeah, I don't like the representations they show here. Like, you can't really show videos in a paper, so it doesn't really mean much. But go check it out. They have a GitHub page. Now, I do want to mention some limitations with this. So I mentioned that you create this canonical image, and the canonical image represents all the objects or all the information, like the object information in the video. Now, you can imagine this can become a problem if something enters the scene. So if I have like a tree that enters the scene, or something that blocks out the ball for a couple frames, the representation here is going to be really bad. You're going to get some weird artifacts around the ball. Maybe the ball is going to be like a little larger, and you're going to get this weird artifact over here because of this part here. And you're going to end up with a really disgusting canonical image that is not editable. And this is something you'll see if you actually use it. So this is one of the limitations. Just something to be aware of. And they mentioned they tried to fix that with SAM, but it still runs into problems. I am curious if this can be, if you can take this method and kind of change it a little bit such that you don't run into any of these issues, but still something I wanted to mention, that this is a problem. If there are weird things, then you're going to run into issues. And if you don't have a still background, like these backgrounds here are pretty much all still, all static. Like the background's the same across all the frames. You're going to end up with weird things or weird artifacts in the canonical representation. Again, so that's another limitation of this method. But I think it's heading in the right direction. And I think it can lead to cool things, just like Nerf. Nerf has led to some cool modeling of 3D scenes. I think this can lead to cool modeling of videos, which are easily editable. But yeah, that's a quick overview of this paper.